Hi everyone. Today we're going to talk about conditions for special parallelograms. These are conditions that whenever they happen, you can conclude that your figure is in fact one of the special parallelograms we talked about in the previous set of notes. Remember that those special parallelograms were rectangles, rhombi, and squares. Remember that the definition of a rectangle was a quadrilateral with 4 right angles. The definition of a rhombus was a quadrilateral with 4 congruent sides, and the definition of a square kind of combined the two. It was a quadrilateral with 4 right angles and 4 congruent sides. So that was just a review of our special parallelograms that we talked about in the previous set of notes. Today we're going to discuss about the figures and how to show that these figures are in fact our special parallelograms. So the first property, the first theorem says if one angle of a parallelogram is a blank angle, then the parallelogram is a rectangle. Now obviously this is a parallelogram because I see that it's a quadrilateral and its opposite sides are parallel, satisfying the definition for a parallelogram. So it says if one of the angles of the parallelogram is a blank, so if it is a right angle, then by one of our parallelogram properties, if the quadrilateral is a parallelogram and it has 1 right angle, then it has 4 right angles. And if it has 4 right angles, then it is a rectangle. So that is because of that parallelogram property, that if parallelogram has 1 right angle, then it has 4 right angles. That's kind of the justification for my theorem. Not that I really need to write it, but I really would like for you to be able to see the connection from this and our parallelograms notes, because that's a theorem from our parallelograms notes. Second theorem says, if the diagonals of a parallelogram are blank, then the parallelogram is a rectangle. So I know this is a parallelogram again because it satisfies the definition of a parallelogram. And it says that segment AC is congruent to segment BD. So my diagonals of the parallelogram are congruent. Well, if my diagonals of the parallelogram are congruent, then my parallelogram must be a rectangle. So that's kind of the converse of our special parallelograms theorem yesterday about rectangles. The next theorem, if one pair of consecutive, so one right after the other, if one pair of consecutive sides of a parallelogram are blank, then the parallelogram is a rhombus. So I have my parallelogram with opposite sides parallel. I see that consecutive sides of the parallelogram are marked with tick marks, so that means that they are congruent. And if that is the case, then the parallelogram is a rhombus. Now this one, we also have the knowledge to talk about why. Remember that on the day we talked about the parallelogram properties, we said that if your quadrilateral was a parallelogram, then opposite sides were not only parallel by definition, but they were also congruent. So if you have consecutive sides are congruent, then that means, well, this side and this side must be congruent. And this side and this side must be congruent. And that means that I have 4 congruent sides, and that's the definition of a rhombus. So this one is because if we have a parallelogram, that means that opposite sides are congruent. Okay. The next one says, if the diagonals of a parallelogram are blank, then the parallelogram is a rhombus. Here are my diagonals, and they have a right angle. So that means that my diagonals of the parallelogram are perpendicular. And if they are perpendicular, then that means the parallelogram is a rhombus. This again is the converse of one of our properties from our special parallelograms notes previously. And then finally, the last theorem says if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. Now at this point, in previous years, we've already talked about triangles and triangle congruence, so we would be able to discuss why this is, but we don't have that knowledge yet. So it's important to know that if you have one diagonal bisect your opposite angles, the pair of opposite angles, then your parallelogram is a rhombus. And this is similar to the converse of one of our properties for special parallelograms yesterday. Okay, so example 1 has 2 parts, and it says determine if the conclusion is valid. So it makes a conclusion and we have to decide yes or no, and we've got to give a reason because we're always giving reasons nowadays in geometry. So the first one says EFGH is a rectangle. Well, look at the picture. I see that I've got opposite sides parallel, so it's definitely a parallelogram. And I want to know if it's a rectangle, so I have this single angle that is a right angle. Well, go back and look at your theorems. Do I have any theorem that talks about if a shape is a parallelogram and it has one right angle, then it's a rectangle? I do. That's the first theorem that we talked about today. If one right angle of a parallelogram is right, then that means that all of the angles are right angles, and you have a rectangle. So this is true, yes. So if you have one right angle of a parallelogram, that implies that you have a rectangle. That's just an abbreviation of the first theorem. Part 2 says quadrilateral MPQR is a rhombus. So we have to decide yes or no. All I know here is that consecutive sides are congruent. So I'm going to go back and see if anything can be used to claim that this is a rhombus. So this one, no, it talks about a rectangle. This one, no, it talks about a rectangle. These two talk about rhombi, and this one talks about a rhombi as well. So do I have one that talks about consecutive sides being congruent? This one talks about bisecting angles. This one talks about perpendicular diagonals. This one talks about consecutive sides. It says if one pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. So we have to have a pair of consecutive sides congruent, and it also has to be in a parallelogram. So I have a pair of consecutive sides that are congruent. Is this a parallelogram? Sure looks like it, but is it marked as one? No, it's not marked as a parallelogram. So you cannot prove that this is a parallelogram, therefore no, you cannot prove that this is a rhombus. So there's not enough information. We need to know if it's a parallelogram. Okay, so let's go to our next problem. It says, use the diagonals to determine whether a parallelogram with the given vertices is a rectangle, a rhombus, or a square. So rectangle, rhombus, or square. Give all the names that apply. Now it does say use the diagonals to determine whether a parallelogram with these vertices is a rectangle, rhombus, or square. So we can assume that the shape that we're going to be drawing with our vertices is a parallelogram. So I'm going to graph the points. -5, -1. That's point A. And B is at -2, 4. C is at 3, 1. And D is at 0, -4. Okay, so A, B, C, D. I'm going to go ahead and use a straight edge to create my parallelogram. Looks good. So step one, nothing else to do. But now I need to determine if it's each of these. So let's talk about a rectangle. Going back to my first page. In order to show this is a rectangle, I can either show that if it has one right angle, I can either show that it has one right angle, and then I'll be able to prove it's a rectangle. Or I can show that the diagonals are congruent. Oops, sorry. So if I need to be able to show if this is either one right angle or the diagonals are congruent, to show the diagonals are congruent, I'd have to do the distance formula twice. To show that this is a right angle, or that really any of these are right angles, then I would have to compare their slopes, because I would want the two segments to be perpendicular. And I feel like I like to compare their slopes a little bit more than I like to do distance formula. So, step two, if I'm determining it's a rectangle and stating my theorem, then I'm going to go ahead and calculate the slopes here. So first I'm going to find the slope of segment BA. There we go. The segment BA. In order to find the slope, I'll do rise, 1, 2, 3, 4, 5, and run, 1, 2, 3. So my slope is 5/3. And perhaps now I'll talk about this side. So I'll find the slope of segment AD. So this is a rise down, so negative 1, 2, 3, and to the right 1, 2, 3, 4, 5. So this slope is negative 3/5. Now, one of those slopes is positive, one of those slopes is negative. The slopes are reciprocals of each other. If I multiplied them together, I would get negative 15/15, which is negative 1. So since these slopes are negative reciprocals, that implies that BA is perpendicular to AD. And that means that we have a right angle. We have a right angle right here. And if we have one right angle, if we have one angle in parallelogram, one right angle in the parallelogram, that implies we have a rectangle. So yes. Yes, it's a rectangle. Let's look at step 3. So we were able to show this was a rectangle. Now we need to show it's a rhombus. So determine if it is a rhombus. State the theorem or definition that supports our answer. So on the first page, there were 3 conditions to be a rhombus. The 3 conditions, we either had to have a pair of consecutive sides being congruent in a parallelogram, and we knew that this was a parallelogram that was given to us. So we either need consecutive sides congruent, or we need diagonals perpendicular, or we need to know that that one diagonal bisects a pair of opposite angles. And that seems to be kind of hard to prove, but why don't we try this one? Why don't we try to show that one side and a side that's consecutive with it is congruent? So let's try that. Let's talk about the distance from, let's do the same 2 segments. Let's do AB. and BC. Oh, I didn't do AB and BC before. What did we do? We did AB and AD. Either one. We can do BC. That's fine. So AB and BC, we want to show that those consecutive sides are congruent. That will prove that this is a rhombus. So if I'm finding a distance on a side, I'm going to use the distance formula. My distance formula is x sub 2 plus x sub 1 squared. No. X sub 2 minus x sub 1 squared, plus y sub 2 minus y sub 1 squared. So my x's for A and B, I have -5 minus -2, so plus 2 squared, plus -1 minus 4 squared. -5 plus 2 is -3. -3 squared is 9. -1 minus 4 is -5. -5 squared is 25. And this is the square root of 34. If I wanted to, I could simplify that, but I'm just going to hold off and see what BC's distance is. So my formula is the same. I'm going to go ahead and insert my values for point B and point C. I have 3 minus -2, so 3 plus 2 squared, plus 1 minus 4 squared. That equals 3 plus 2 is 5. 5 squared is 25. 1 minus 4 is -3. -3 squared is 9. And 25 plus 9 is 34. So even if I don't simplify this, I see that AB's distance and BC's distance is the same. So, since I have consecutive sides, so one pair, consecutive sides, congruent in the parallelogram, that implies that my parallelogram is a rhombus. So yes. And finally, I need to determine if ABCD is a square. Well, if you remember from the last set of notes that the definition of a square is a quadrilateral with 4 right angles and 4 congruent sides, we already determined that this was, yes, a rectangle with 4 right angles. We determined that this was, yes, a rhombus with 4 congruent sides. Therefore, this is a square. Yes. It is a rectangle and rhombus. So now I have to give all the names that apply. So yes, it's a square. That's the most specific one. It's a rectangle, it's a rhombus. So those are all the special parallelograms that we talked about. In fact, just by mentioning that, if it's a square or a rectangle or a rhombus, by default, it is also a parallelogram. And a parallelogram is a quadrilateral with opposite sides parallel. So not only is it a parallelogram, we can also call it a quadrilateral.